Good afternoon, everyone. Looks like people are getting settled into the room here. I'm Mark Rowe, research scientist with the University of Michigan Siler. It's my privilege today to introduce our speaker for the Siler Great Lakes Seminar Series, Dr. Bopi Biddanda of Grand Valley State University Annis Water Resources Institute. Dr. Biddanda is an aquatic microbial ecologist and carbon biogeochemist studying the movement of carbon driven by microbes in freshwater ecosystems. He earned a PhD in ecology from the University of Georgia, where he explored new mechanisms of carbon flux mediated by microbes in the sea. He has numerous subsequent research experiences at institutes in Germany, Texas, Brazil, and Minnesota. In 2009, he was the recipient of the Chandler-Misner Award from the International Association of Great Lakes Research. So we're excited to see his seminar today, the title of which is Finding and Tracking the Goldilocks Zone for Carbon Cycling in a Great Lakes Watershed. I'll turn it over to you, Bopi.
Thank you, Mark, and thank Siler for this invite. It's always nice to be back at GLUR. It's not working, at least talking. Okay. I put this fairy tale here because it is related to the talk about finding the Goldilocks zone. As you know, Earth is in the Goldilocks zone according to NASA, right? And we are constantly in search for other planets in the habitable or Goldilocks zone elsewhere. I still get excited reading this because my mom, who's a botanist, used to read it to me when I was very, very little. Ecosystems have Goldilocks zones too. And the story we'll be going through is finding one and tracking it. So that's us, the Great Lakes watershed. And this is the site of our study focus, watershed, the Muskegon River watershed, the portion in orange. It's the second largest watershed in Michigan, joining the second largest of the Great Lakes, Lake Michigan. And all of you know that the balance of carbon in the biosphere is made by the balance of photosynthesis and respiration. Okay, it's basically the planet's breath. And in these Keeling curves, which is very iconic and which really is a backbone of climate science now, more than 50 years old, it's clearly showing the breadth of the planet. The ones in the northern hemisphere showing the growth of the deciduous forests in the spring, which is the drawdown of carbon dioxide, and then they spit it back in the winter as leaves drop and things go dormant. And so you have lesser oscillations in the equator and in the south and so on, where there's not that much terrestrial influence. We have a 40% increase in carbon dioxide rise. Fortunately, carbon dioxide is only 0.04% of the atmosphere. Okay. So you can, because it'd be bad if we had the same amount of oxygen. Fortunately, we have 21% of oxygen, but there's an equimolar drawdown in oxygen too. Okay, so this equimolar dance between these two major elements is what makes life possible since the very beginning of Earth. So this William Schlesinger's saying there, the storage of carbon and release of free oxygen are the essence of life, is not only philosophical, but is very, very deeply scientific. The reason I point out the oxygen relationship is very few are aware of that drawdown. Okay. And it matters. From knowing the drawdown in oxygen or the rise in oxygen, you can figure out the carbon cycle, because the opposite is happening with carbon. So this is between like 3 days curve. Oxygen goes up during the day and comes down during the night, goes up during the day, comes up during the night. So photosynthesis and respiration cycle. This is the lake's breadth. And while reviewing then new book on aquatic respiration in aquatic ecosystems, after having a few beers, I wrote this: photosynthesis and respiration are the yin and yang of the biosphere. And the editor published it. It's again pretty deep when I think about it, but probably was the effect of the beer. So to come back to the carbon cycle, for a long time, the aquatic ecosystems in the biosphere didn't figure it out. They were just passive pipes. In the scale of the big terrestrial and the even larger oceanic pools, the aquatic ecosystems were just didn't amount to much. They were passive pipelines. That's the traditional view painted in the top, where it's just a passive pipeline. But recent reviews, this is a 10 years old review by Cole et al., clearly show that there's a couple of gigatons of carbon coming in with only about 1 going out, and a lot being respired, okay, and significant amount buried. And I'll show you that these amounts, although they may look small, they're big. This respiration of aquatic ecosystems, freshwater systems, is enough to offset the net drawdown of carbon dioxide from the entire oceans. And this burial of carbon is more than the entire amount of carbon being buried in the ocean. So freshwater ecosystems are very reactive, not passive pipes at all. And we have a review coming up in years that shifts this paradigm. Okay. In this, I point to some question marks. We really don't have good grasp of how much carbon is coming into freshwater systems. We also we have a poor handle on what's being respired, although it's pretty big. You can see that that's about 1.5 on the average, which is more than the NPP of the oceans. Okay. And we have not a good handle on how much is being fixed by freshwater systems. And this burial of carbon is huge. It's more than twice by conservative estimates of what's being buried in the vast ocean floors. Definitely plays a very important role in the oxygenation of the planet. Okay, that curve that we saw, the carbon oxygen drawdown, would be even more steeper if we didn't have this freshwater carbon burial, for example. So coming back to Lake Michigan, where we do our work and then try to put that into the overall context, we have a dynamic ecosystem. Even though it's a large lake, it's not got, Lake Michigan has only got 100-year residence time, which is a human lifespan, and even distant regions of it are influenced by terrestrial influences, like terrigenous inputs. So in this old study that was published in Ecosystems a long time ago, we demonstrated, accounting for all the inputs from the rivers into the Lake Michigan basin, we demonstrated that about 10% of the carbon sources for all the bacteria in the water in the Lake Michigan, and about 20% of the phosphorus needs of phytoplankton in Lake Michigan come from not within lake sources, but from external subsidies. So it's very important that it's still true that internal recycling rules, but external forcing is very vital component of the, you can imagine, year-to-year variability and what even becomes net productivity, what the fishes see and what fishermen take and so on, and the blooms that follow and so on. So the connection between the water, life in the water, and the terrestrial subsidies, which is, I'm arguing, is very important, both in terms of organic inputs and inorganic nutrient input. The real connectors are microbes. Okay, and I'll introduce that concept with the party napkin, which is a dangerous thing to do. And the second and third lines here, I don't know if Ben Franklin said it, but the fourth line is really true. Okay. It's a fact. There is 1 million living cells in a milliliter of water, be it from Lake Michigan, be it from your backyard pond, or from the Southern Ocean or the middle of the Pacific. And in this image, what you see is the tiniest dots that you can barely see are viruses. There's about 10 million of them in a milliliter. And then you see the bigger blobs. They are either heterotrophic bacteria or cyanobacteria. And you see some are attached to a diatom. Okay, that could be like a aqua ship, and it's like a spaceship. And these could be aquanauts riding on a ship that's also their food resource. So it's really true that no one on this planet knows what's happening in a milliliter of seawater. You can imagine these million cells are not just sitting there. Most of them are going somewhere, doing something. Okay, they have jobs to do. I mean, very simply, they have the jobs of, many of them have photosynthesis to do, all of them have respiration to do. So you can see how complicated it gets in just a milliliter of seawater or lake water. And we're trying to understand whole ecosystems, whole oceans, so the challenge is immense. Okay, we tried to keep the problem simple. We are in this study that we ran for more than a decade, from 2002 to 2013, we have followed the metabolism, photosynthesis and respiration from up in the watershed here in Muskegon Lake, and actually we have a creek station too, Cedar Creek, all the way down to the 110-meter isobath, which we call deep water in Lake Michigan. These are also standard Eagle or Global stations, which are occupied on every major cruise. And those results show a very interesting thing. Nothing that you wouldn't expect. Everything declines as you go away from the land into the oligotrophic. And we have gross primary production, it's going down. We have respiration, that's going down, but not as much as the gross primary production. Okay. So as a consequence, net production almost zeroes out in the offshore waters. Okay, and that's also why they are oligotrophic. Okay, there's not much biomass. Whatever is little is produced is consumed. This presents interesting biogeochemical considerations. If you have more respiration than production in offshore waters, that makes it a potential carbon source, right? Also begs the question, where's the fuel for that coming from? You can't respire nothing. So that's where the big imageries I showed earlier, the lateral transport of material from coastal water to offshore waters, the riverine plumes, all that come into play. And they could be also living on past primary production, like spring production that's lingering on. Those are just potential explanations. None of this can be really verified unless you have close time series observations. These are just monthly observations. So to draw a schematic of that, you can assume nearshore systems are carbon sinks, whereas offshore systems are carbon sources, just because they seem to have a net respiration going on with near balance net primary productivity. And it's not only that we have reported this for this watershed. There are reports now that all of world's coastal oceans are becoming net sinks for organic matter, for carbon. And that is it might even be a recent phenomenon, whereas they were net sources before, they're becoming net sinks now. And it's probably one of the inadvertent effects of anthropogenic nutrient pollution to our waters. They're becoming net sinks for atmospheric carbon. So in a way, what we are unintentionally doing is probably buffering the excessive increase of carbon dioxide in the atmosphere. So in that whole watershed range, going from Cedar Creek all the way through the Muskegon River, Drowned River estuary to offshore waters, one of my students, Deb Dilla, she found out that Muskegon Lake has, over the year, has always the highest amount of chlorophyll, and it has the highest amount of net productivity. Okay. That's why we call it the Goldilocks zone. Not too little, not too much, just right. And yeah, there's a tendency by the creek and the river to be almost net heterotrophic, meaning more respiration than this thing, than production. But in Muskegon Lake, in this intermediate zone where there's the right amount of inputs and the right amount of residence time, like nearly somewhere between 3 weeks to 1 month, the right combination of times for invertebrate life cycles to complete. So there is a good biomass and it's not so big migratory corridor for fishes and so on. So it is just like it's the right optimal condition in this watershed. I believe every watershed, every ecological transect will have a Goldilocks zone, something like that, optimal zone. And continuous measurements, like discrete measurements every month made, reinforce this story. There is GPP, the gross primary production, there's respiration, which peaks up later, and so there is net productivity here and net respiration here, and this is the ratio between GPP and R. Anything above this one line means there's net productivity. And we painted some scenarios of how a classical food web might go through the spring diet and bloom, gradually zooplankton and fish, and everybody being happy, to the in excessive nutrient conditions, cyanobacteria growing and causing issues, and the late fall snow down. And there's on both ends of the spectrum, there's the winter siesta or winter nap. So it's nice to have discrete measurements, which are hard work. It'd be even better to have time series observations, isn't it? These lake ecosystems are very complex. When you try to put all the things in one picture, it's very complex. There's inputs, outputs, things happening inside. And so we dreamed up an observatory that would do the job for us when we can be resting, okay, not doing anything. There's a mean storm blowing through here, but we could watch what's happening to the lake. How does it mix from the shelter of our computers? So this is the kind of observatory system we got going on for, this is the 7th year of operation, and that will be the story I'll tell from now on. So this is the observatory we have in the middle of Muskegon Lake. It has a few simple objectives: to set up a system to continuously measure all parameters that we possibly can, the meteorological and water quality parameters, link the data extensively to regional and other networks, and strongly enable not only research, but also education and outreach. So that's the buoy in the middle here at the 12 meters, and we have 3 other spar buoys with temperature strengths, the green ones. One in the east, one in the south, and then one in the west. We also have temperature strengths, and this year we'll have DO as well in the channel, and also in the main branch of the Muskegon River, the north branch. That's the nuts and bolts of the system, so how it would look if you're a fish, okay, including it's also combined with an ADCP that looks upwards and interrogates the water column. So we have 4 clusters of sensors, one at 2 meters, one at 6, one at 10, and one at 12 or so, approximately. And several T nodes at every meter, so we have more temperature than other data. Just to give a flavor of the instruments that we have underwater as of now. And the system is, for this year, is alive and reporting data online. And that's very simply how we get the data into our computers through a cell phone telemetry, and then it's also backed up in a Grand Valley hard drive and then sent out to other systems such as GLOS, which is the regional hub of the Global Ocean Observatory Network. So we have it on display in the foyer of the institute. So our students and faculty, when they go out for field sampling, they can just check the current weather conditions. In fact, fishermen and sailors use it. If our system goes down for a couple of hours, we get a lot of calls. It makes it a little bit intensive. We got to go fix it, but at least it's close by, so we're able to do it. That's the lab display of this system. And we have a very friendly website. So yeah, usually you just have to go to the current conditions here, and then you can actually plot interactive data. You can choose your variables, the interval and the variable. You can even plot X versus Y, like temperature versus chlorophyll. And you can get data like this. Just want for an example data. This is from 2011 and 2012 summer data, and you can see two contrasting years during a wet year and a dry year. We have roughly the same amount of chlorophyll, but on the wet year we had high phycocyanin, which is a harmful algal bloom signal pigment, and that's also complemented by the high turbidity we have, which means there are a lot of runoff that year. I don't know if this idea that more runoff equals more HABs is universal, but that's kind of observations you can make and see if they persist over different years. This is the kind of data we get for for temperature, oxygen, and so on. So we are seeing clear indications of recurring hypoxia. So basically, the surface waters warm up, the bottom waters also warm up, but once it's stratified, they stay cool or stay cold, and then fall mixing again makes them all the same. And the pattern repeats. And here the blues are surface water DO, and the reds and the blacks are deep water DO. And you get sometimes you get the intermediate water having less DO than the bottom water, and that we'll get to that later. There is oxygenated Lake Michigan water intruding during coastal upwelling that's causing this. At least that's what we believe. So I'm writing a paper for JGLR now on the recurring hypoxia in this system using very simple data like this with repeating stratification, biomass production, followed by the evolution of hypoxia. At least about a quarter of the lake bottom experiences, in terms of volume, experiences hypoxia over a month or two each year, and that's pretty significant. And to imagine that we had a research station right there, and we didn't really have a good idea about this for a couple of decades before the observatory came on. So that's one example of the power of repeated automated observatory. So I'll run through evidence for recurring hypoxia in bottom water in Muskegon Lake. So from years 2011, those are highlighted in blue, all the way to 2015 in this sequence. So that's for 2012, 2013, 14, and 15. So there's no doubt it's happening. It happens differently each year. It has got, it depends on the warming, it depends on the wind mixing, and so on, and also intrusion of water from Lake Michigan, and maybe even river runoff, but it's happening every year. My students looked at, Anthony looked at the abundance of number of fish and also species of fish. These are number of species of fish he caught on different months during the summer into the fall. Yeah, we put nets, gill nets in the bottom water in the hypoxic zone or hypolimnium. And as you can see, with increasing, this is the DO line, dissolved oxygen line. You can see both the abundance and the number of species got decreased during the during that. So it's basically habitat compression or exclusion of fishes from 1/4 to 1/3 of the lake. So, yeah. And then even for microbes, it has consequences by shifting redox. So Anthony will be presenting some of these results at next week's IAGLA. This is one of his data showing some evidence for actual Lake Michigan water intrusion. And that is the part here you see. In the early part of late June to early part of July, you see bottom water temperatures dropping sharply at the observatory, which is in the middle of the lake. And dissolved oxygen increasing sharply. And then we have something similar that happens during wind-driven mixing too, where bottom water temperature drops and oxygen content increases. But those are brief ones, and those are closely correlated with high-speed winds, like 20 knots for 6 hours or more. That's what it takes to get the lake mixing. But this one seems to be very clearly a sign of upwell cold coastal water, Lake Michigan water up getting in through the channel and intruding all the way in near the buoy station, which is the middle of the lake. And so it's actually will displace previously existing hypoxic cold water with the colder oxygenated water. So suddenly you have a bottom water that's more oxygenated than previously. So last year we deployed Katie Knapp, my graduate student, we deployed some temperature strengths this is the Muskegon Lake channel, where the estuary exits into Lake Michigan. And we have some interesting observations. At the channel, you can see at 4 meters, you can see some examples of cold water intrusion. And it persists in deeper waters. There are other smaller intrusions. We have not verified them. And in the west station, which is closest to the channel, you see signals of the intrusion in the deeper waters. Okay. A little bit here. In the south station, which is the deepest part of the lake, also see that signal coming through. And I think as far as the east station, which is close to the river itself. So this is a lake-wide intrusion. Once it starts going, it will percolate all the way through. And when you think about it, it might be a really nice part of this whole Goldilocks story. Hypoxia would have been more severe and long-lasting, with larger impacts, negative deleterious impact. But for this episodic intrusion of huge amounts of cold oxygenated Lake Michigan water. So it's a very dynamic system, almost like the salt wedge intrusions into marine estuaries. There is this episodic intrusion of cold oxygenated water. And we also have evidence from low conductivity that it is actually Lake Michigan water. I had a postdoc, the Cookman, who put this data together. This is for 2015, and Muskegon Lake temperature, you see in this region in mid-July, bottom water dropped by about 10 degrees Fahrenheit. These are in Fahrenheit. And dissolved oxygen increased at that time. And at the nearshore buoy, that's I think the M10 or something that Gruber runs from this lab, where we also have DO sensors on it, we noticed a drop of more than 10 degrees Fahrenheit. That's upwelling water, cold water. So there's a nice synchrony there. And then he went on and looked up this satellite imagery data for compilation for surface temperatures. And at that time, you do have on July 2nd, which is like just days before, you have upwelling water, cold water in just offshore of Muskegon Lake. So nice proxy evidence that it is the cold upwelling water that might be intruding. And we drew a scenario, and he's writing it up for limnology and oceanography, So during cold upwelling times, temperature, cold water seeps in, and temperature gets low everywhere, including all the way into the middle of the lake, and it oxygenates the otherwise hypoxic soil. And Shenshen Lu, who is with you here now, she's done a lot of work on developing hydrodynamic modeling of this system. She'll present too at IAGLR next week. And I'm not very competent to explain all this, but she used this schism model with huge number of elements and nodes to get high resolution modeling of this system. She has dynamic videos of how this works. Right? But very simply, she also sees this. This is within a couple of weeks time in September last year. Evidence for cold deep water intrusion into Muskegon Lake. And then it slowly erodes away as the riverine input begins to dominate and push it out. We also have that upward-looking ADCP that has been able to reveal a lot about how the inner workings of this system. During normal times, the flow is unidirectional, like a river, but it can change depending on the winds and so on. And for example, this is a good example of during when it's couple of years we've deployed it during ice cover in the winter. And you can see it's very uniform. The flow is laminar, and it's just like this estuary is decided to be a river now. Okay. And then during the summer, it's confused. It doesn't know whether it's a river or it's a lake or an estuary. It's sloshing back and forth. That's what these are daily oscillations. So usually there is land breeze during the afternoon with the low pressure on the land, so it goes one way and comes back the other way at night. And then storms, episodic storms, these are just mixing all the way to the bottom on occasion. Also are very nicely tracked. So hopefully we will use these data more powerfully down the road. In addition, we are getting 3 buoys, ADCPs this year to deploy at the south, at the east, south, and west locations. So that should give us a more synoptic view of how this lake works. And we have evidence that the lake changes its height by about ½ meter during strong winds. For example, strong northwest winds will pile up water on this end near the institute. And there's a difference of nearly ½ meter from the one edge to the other. So you can see when the wind lets go, it's going to C-shape back and forth, and that has consequences for maybe needing the hypoxia zone this way, that way, and so on. And so there's lots of challenges, of course. These systems are not just something you throw there and forget about it. Luckily, we have good people behind this. We go off and clean up the mess. We have various things working for us that helps us. We annually apply this ablative biofouling paint, which is pretty toxic, and it's ablative. So as soon as you get a thick layer of mussels or bryozoans, that layer peels away. We paint multiple layers on it. And it's got lots of copper guards everywhere, and we got the usual wipers and so on, but clean surface on this Suna, you can see. It's interesting, but sometimes things are overwhelming. Yeah, mussels and bryozoans, especially in the surface waters, is our worst, the thing that takes a lot of maintenance. So the data by themselves may not be alive, but they're beautiful, especially when they sing a melody, when they can catch the season. Like in this case, what we're really seeing is an average day in Muskegon Lake at the buoy in April, for example. There's these ones. Let's focus on, let's say, September, which is a dark number. The Devo cycle goes through like this. At midnight, After midnight, it comes down. Then during the day, it grows and flattens out, and it repeats. Sunlight does this intermediate this thing. It's September, already lights are fading. And wind speed, it's an average day, generally picking up during the afternoon. So plots like this let you see the average day in the life of Bopi or something. That's what you're seeing, the average conditions in a day. I thought it was very interesting. My student Leon Giroux drew this, and it was beautiful. And there's more beauty in these natural rhythms, how you can catch this. Oh, I was at the March for Science, and one of our lady colleagues had this interesting poster. But I think, we should turn around. You harness the power of these observatories to really, this is science. If it's carefully done, doesn't require statistics, because the instrument is measuring every 5 minutes the met conditions, every 15 minutes the water quality conditions. It is very powerful, and this part of the story that repeats the seasons, and then you can look at reasons for interannual, interday differences, and so on. So there's a wealth of information that comes from this. I worked for 3 years with this ecologist philosopher at the Alfred Wegener Institute in Germany, Victor Smedacek, and I think he said it very, very well. So I think I'm going to leave you with that and hopefully take questions. Well, lastly, I should acknowledge my collaborators and funding agencies. Should say it's a 7-year project now. For the first 3 years, it was EPA funded, and I am aware of very few projects that have lasted for 4 more years beyond that. And especially the 4 more years beyond that could be called a GLERL Seiler project, actually, because it's been sustained by support of various kinds, in addition to money from here. We still run it on a shoestring budget. We're able to run it from a small institution with small people for something like less than $36,000 a year. I think it's a very good return for the money. And as you know, the data is not hogged by us. It's universally available. As of now, every nation on the planet has accessed this data. I don't know how they've used it, but we are aware of school teachers in the area using it to see, oh, how did the lake wake up this morning? Did it sleep yesterday? Did the oxygen increase, go down with the day and night? Those kind of questions. Temperature and other variables, and harmful algal blooms, hypoxia, and things that make a connection with the people. Anyway, thank you so much. Yes, Hank.
Question on this. I've seen a lot of this stuff on carbon cycling in a number of venues. Has anyone really tied in the whole nutrient stoichiometry story here? We're not really just looking at carbon, phosphorus, and nitrogen are driving a lot of this Goldilocks zones and the respiration and oxygen consumption. Are you beginning to tie that together?
No, I myself am not. But I'm aware of other people like Sterner's group and all trying to do that in Lake Superior and so on. Well, there is a stoichiometric story, yes. I am personally not pursuing that. Yeah. Nutrients are definitely connected. Organic matters, we're in very simple terms, heterogeneous organic matter coming into an ecosystem will drive respiration. Heterogeneous nutrients inorganic nutrients coming into that system will drive primary production, assuming they're limited for those things. Yeah, that's the very basic broad stoichiometry. Maybe I'm at the limit of my understanding to answer that question. Yeah. I think Brad.
Bopi, nice talk. I really enjoyed it. I'm curious about the idea that coastal zones are carbon storage areas where the offshore zones are potential sources. In the coastal zones, do we have any good ideas from your system or others of what the residence times are? Do we know if that carbon is actually getting buried on time scales where it's keeping it out of the atmosphere, or is that just matter that's getting decomposed next year? Do you know?
I really don't. But I think the kind of coastal zones we're talking about are big and broad coastal zones. And I think there is as long as there is a net drawdown and deposition into the sediments, they will be removed at least for decades, if not centuries. Yes, even in Lake Michigan, we have sedimentary suspension and things come back into circulation. But it doesn't happen universally, it doesn't happen repeatedly. So once things get buried, there's more chance of them getting buried into the anoxic zones, anaerobic zones, and getting preserved. So I think the tendency for the world's coastal zones to have switched and gone into a net carbon burial stage is real, because there's enough reports of this happening in other parts of the coastal oceans, and I think it's here to stay. And I can say it's almost certainly a human-made shift. Yeah, they were all actually are more or less either neutral or positively carbon sources before, but since nutrifying our coastal waters, there's been more productivity and more room for that fallout to get buried in the sediments. Yeah, it's possible to assume that respiration in the sediment has increased somewhat as well, but the burial is overwhelming, has overwhelmed that respiration rate. So there's net burial in the coastal sediments. Yeah. Well, thank you very much.